So let's first talk about a few issues that might happen when you want to use gradient descent. So if you want to use the gradient descent, the function that you have, and you want to just minimize, that function needs to have gradient, right? So this means that the function should be differentiable. And many functions that you have in practice are not differentiable. The most simple one, if you just consider the perceptron model, the output of perceptron is calculated by step function, right? And that step function does not have gradient, right? So it's just jumping from 0 to 1. You cannot simply take the derivative, right? So that issue is the key issue that sometimes make us decide for example, activation, for example, how to combine different information in a network, because you always need to have a gradient if you want this algorithm to work. Many people in deep learning, when they talk about flow of information, they always think about flow of gradient. It means that you need to have operations which, when you take the gradient, when you take the derivative, you need to see something non-zero. Because if it's 0, then essentially that algorithm is not going to work, right? So two major cases that could happen in practice. One of them is that your function is continuous. It means that it's not having any jump. It's just continuously going up. But it's not differentiable. It has a bunch of edges. If that happens, it's not an issue. You can always handle it. But if your function is discontinuous, it's not continuous, it has a jump, then the problem gets more challenging. Okay? Now, I'm going to give you just a kind of clue about what you can do. In practice, I do know that all of you always use PyTorch, but it's good to know what happens, like how PyTorch is handling this. And if you see any weird behavior, then you know probably where you should look at. So the first thing is that when you have a function which is continuous, but it's not differentiable, like ReLU function, right? So ReLU function, this is the function. We said it's 0 anywhere when x is negative. And then when x is positive, it's going to be a linear function, right? On this side, you have a gradient which is 0. It's not the favorite gradient that you want, right? On the other side, you have a gradient which is 1, right? If you take the derivative at any point positive, it's going to be 1. But the issue is that at point x equal by 0, you have an edge, right? And if you plot the derivative of the function, you see it's jumping, right? So you have gradient at x negative, you have gradient at x positive, but you don't have gradient at x equal by 0. And it could happen in many functions, like the function goes smooth, and then you're going to somehow break, and then it's going to keep going, right? So that's going to happen. Now, you might tell me that, well, at the end of the day, we want to take the gradient of the risk function, right? But the risk function is computed out of the output of your neural network, right? And the output of your neural network is computed using the activation function, for instance, ReLU, right? So this means that when you start taking the derivatives, at the end of the day, you need to take the derivative of this ReLU function as well, right? And this is the point where the problem could happen, right? For this particular case, we don't have any problem, essentially. We can use what we call it subgradient. So what is the idea of subgradient? You might say that, the definition is that if you just plot a curve which is smooth, and it's just taking your original curve, original function, above it, and it's touching your function exactly at that particular point, then instead of using the gradient of your function itself, you can use the gradient of that smooth under function, the lower bound. So look at this guy here. So this is the ReLU function, right? If I draw this line, this is going to touch the function at point 0. At any point else, the function is above this function, right? Everybody sees that? Right? Now, what is the slope of this line that I'm drawing, the gray line? What is the slope? Smaller than 1, right? So if I draw any line with a slope smaller than 1, it's going to lie there, right? If I increase the slope more than 1, it's not going to happen anymore, right? It's going to just cross the point 0 above this other line, right? So it's going to cross the function. It's not going to bound it from below, right? Now, any of those lines is accepted as a kind of lower bound. and you take the derivative of that line at point 0 instead of the derivative of your original function, and it's going to work. This is what we call it subgradient. Like it's a function which is always like behaving as good as the other function because it's just bounding it from below, right? It's touching your function at that point. So it means that if you take the gradient of that guy, it still gives you a good direction to go, right? So that's the idea of subgradient. So essentially, any line with a slope less than 1 is going to be an acceptable line. So you could somehow think that the gradient here is 0, the gradient here is 1, and any point between 0 and 1 is accepted as the gradient at point 0, right? So if you want to define this gradient on your algorithm, if you want to just implement it from scratch, then you can just put any number between 0 and 1, and it's going to work always, right? Typically, we put it 1 because we like large gradients, right? We want larger gradient to just move faster. So this is the first case, but the other case is the case where we have discontinuous function, right? And the discontinuous function is not as easy as the other one. The reason is that just looking at ReLU function, when I am moving from x negative to x positive, I'm not jumping, right? So the change in the function is still very small, right? But it's just not behaving smooth, right? This is different from here, right? If I want to define the derivative here, what I could say at x equal by any number negative, right? Close to 0, but negative. It's 0. At point x equal by 0, it's 1, right? Or any point after 0, it's 1. Now, when you make this tiny interval, it doesn't matter how tiny your interval is, you always jump from 0 to 1, right? And then if you just write down the definition of the derivative, you cannot write down, the limit is going to be infinite, right? So what you can say the function has no change here, so the gradient going to remain 0. At point 0, actually, you cannot mathematically define the gradient, but if you want to think about it, you can say it's a kind of huge step function, right? It's a jump. It's a Dirac impulse, right? The value of gradient somehow is infinite at this point, right? Now, if you want to use gradient descent and you want to just replace this intuitive idea there, it's not going to work, right? Because infinite gradient, it means that you update with the step infinite, and this is like just shooting your function somewhere wrong, right? What we do in practice, so the gradient is infinite, and we can really do not do this. What we do in practice, we usually avoid such functions. We can keep edgy functions, non-differentiable but continuous, but we usually avoid discontinuous functions. But if by any reason you want to use it, then the only idea that you have is to just reuse the sign of the gradient at that point. So you're going to say, here is plus infinity, so I'm going to take it plus 1, right? And if the function is just jumping from 1 to 0, you can just put it minus 1, right? You can only use the sign. Now, if you only use the sign, does it remind you of some specific algorithm? Perceptron algorithm, right? So when we wanted to just train perceptron, if I wrote you the perceptron algorithm by Rosenblatt, right? And in the algorithm, you was just in each step, when you find an error, you update with the sign of that z, right? And the sign of that z was essentially the sign of this infinite gradient, because you had step function, right? This was the point. I'm not sure if originally Rosenblatt wrote it down based on gradient descent, or he just intuitively derived that. But essentially, if you write down the gradient descent and just you take the sign of the gradient, then it's going to give you the same thing. Okay? So this is why I told you that we typically avoid step function as an activation. You can also guess why I told you that error function, like the error indicator that was used in the perceptron algorithm, was not a good choice of the loss function. Because at the end of the day, your empirical risk is computed out of the loss function. And when the loss function is that very weird non-continuous function, just giving you 1 or 0, then it's very hard to take derivative of that, right? So you prefer to have more continuous functions which give you gradient values, right? So everybody's clear? Questions? So I do know in practice, as I told you, you usually use some available library to do all the gradient by some sort of autograph. But the point is that if you see something weird happens, you can just suspect this issue, right? If you're using a function which is discontinuous, that might cause some issue in your design, right? Great. So if you got no question, then let me now answer the other question that I initially mentioned. So in practice, we have three different kinds of points which have zero gradient, right? And if you think you are just lying on any of those points, right, your gradient descent is not going to update anymore, right? Because the gradient is zero, then your function is not going to change, right? But I just want to convince you that in practice you never end up by anything but your minimizer. So let's look at this guy, right? This was the algorithm that we had. And in the algorithm, as I said, we are just updating with the gradient. So if we set this epsilon very small, then essentially we are going to end up with a point. So this algorithm is going to stop somewhere where your gradient is essentially zero, right? Practically zero, very close to zero. And such kind of points could be a maximum, minimum, or a saddle point, right? So any of those points is having gradient zero. This means that any of those points, if you get it into that point exactly, that blue gradient is going to be zero. Then your WT is not different from WT minus 1. And because of that, delta is going to be 0. And then your algorithm is going to stop, right? Everybody's cool, right? Now, the first thing, let's look at maximum. Okay, so let's look at the maximum. Say that I exactly land on the maximum point. What I told you before is going to happen. But in practice, if you start from a random point and you keep updating, do you expect to exactly touch that maximum point? No, right? So you're going to land somewhere around that point. What's going to happen if you land somewhere around it? So in practice, I'm going to land somewhere around it, right? And when I land somewhere around it, minus gradient is always pushing me towards the point where the function decreases, right? That means that if I just land here at this particular point, which is very close to this maximum point, then the gradient tells me just go out, right? So you're never going to get trapped at that point, right? There is no direction telling you go towards that maximum, right? It always tells you go outside, right? The only case that could happen is that you exactly touch this blue point, which is practically never happening, right? So it's just you touch one particular point on the real axis. That never happens, right? So if you use your algorithm to update, maybe the chance of just touching that one is 10 to the power minus 100. I don't know. Something like that, right? And it never happens in practice, right? So in practice, you are never going to touch that point. You always get out of the maximum point, right? Cool? Yeah. What about so practically, no maximum is going to happen. What about the minimum point? It always tells you go inside, right? So again, you are not going to touch that red point exactly, but the point is that if you just land anywhere close to it, your minus gradient always tells you just go towards that, right? And then you might again land somewhere close to it, and it's going to again tell you go towards that, right? You keep on going, right? You never stop going toward that, right? So this means that you are essentially going to get trapped at this bowl, right? And when you use gradient descent, you can get to the minimum point, definitely, right? Everybody's cool, right? You see it? Now, what about the other case, the inflection point? Inflection point, sorry, not inflation. The inflection point. So if you have inflection point, again, you have gradient 0, that thing could happen, but you always need to think about what's going to happen in practice. In practice, you are not going to touch that point exactly, right? So say that I land somewhere close to it, like this one, right? This guy is always telling me to just go outside, right? If I get here, anywhere before it, right? This is telling me to just move towards this one. But again, the chance that I move and get exactly here is pretty much 0, right? At the end of the day, I am going to just oscillate around it, right? And I don't need to oscillate. I mean, once I just touch a tiny bit out of this point, I'm going to get outside, right? So again, the chance of getting trapped at this point is very small, right? So in practice, you again do not land here. Even though, just in brackets, this is more likely to get trapped as compared to the maximum, right? Because in the maximum, wherever around it, you're just getting outside, right? Here, you first get towards it, and then you get outside, right? And there is a tiny bit of higher chance that you trap here, but I told you that one is, I don't know, 10 to power minus 100. Maybe this one is 10 to power minus 90, okay? Who cares, right? Yeah? Yes? Yes, you can do it. Yes, you can use perturbation, right? You get your point, and you just randomly move around it, right? And then you let the algorithm run again. If the algorithm runs again and it gets back to the point you started from, it's going to say this was a minimum. If not, then it's going to get out, and now that you were trapped here. I mean, this one-dimensional case is not really something that easy to see, but in the saddle point case, when you have a multidimensional function, then this could happen 1 out of a million, that you just land in a saddle point. But then you can just simply randomly move it in all directions, so to make sure that you're going to get back to the point, right? Yeah. Yes?
So in practice, is it easier for us to use gradient descent to identify inflection points, since it never stops?
To identify
Inflection point, since the gradient descent always go left or go right.
yes, but you mean that you use the algorithm to find this point?
Yeah. For example, in the other algorithm, we find, for example, first derivative equals 0, and then we are using gradient descent to identify whether it's an inflection point or
Actually, if you want to find out whether it's inflection point or not, you need to take the second derivative, right? If the second derivative is again 0, then it's inflection point, right? Okay. But the sign of the second derivative is going to say what kind of saddle point that is, right? So if it's positive, then it means it's negative. It's minimum. If it's negative, it's maximum. If it's 0, then it's inflection. Okay. Yeah. Questions? No question? Okay, cool. So that is about the inflection point. So again, practically, your algorithm is not going to end up with an inflection point. One thing that you might tell me, and this is totally right, what about the saddle point? And about the saddle point, the story is a tiny bit different. So a saddle point is something like this, right? I told you before. So in one direction, or in a couple of directions, when you think high dimensional, in a couple of directions it's minimum, in a couple of other directions that is maximum, right? And the name saddle comes from the fact that the saddle on a horse looks like that, right? So this is a saddle, this is where you see it, and then if you look from this side, then you're going to see a minimum, right? But if you look from this side, right, front of the horse, then you're going to see a maximum, right? So this is the saddle point, and the question is that, are we going to stay within the saddle point if we get close to it, right? Now, that could happen, but the chance is, again, extremely low. How does that happen? So, yeah, if you land exactly on the saddle point, you're going to stop, but in practice, we always land somewhere around it. And what's going to happen if we land around it? So if we land around it, so it means that this is the point where you see this behavior on one side and this maximization behavior on the other side. Now, if you land somewhere around it, and in that direction, you only have gradient, which is moving in the direction of your minimum, right? So say that this is the case where the minimum is, right? This is the direction where the minimum is. And this orthogonal direction is the direction that the maximum is, right? So if you land somewhere around your saddle point and you only have gradient in the direction of the minimum, right? like the other entry in your gradient is absolutely 0, then you are not going, you are obviously going to move towards that saddle point, right? Because you are moving actually only in the direction where the function is minimized, and then you can land at that point, right? But again, in practice, this is very low chance. If your function is extremely high dimensional, and your saddle point is extremely special, like it's in many directions minimum, but in a few directions maximum, right? If that happens, then it could happen that you're staying within the area of the saddle point because, for example, your gradient is very, very tiny in the direction that the maximum is happening. But that is, again, in practice, very rare. Like, I personally have not got into an algorithm I suspect that is in the saddle point, right? So this is pretty much one of the last things you want to check in your implementation, but it's not the case that it never happens, right? So can we land in such a point which we do not have really a gradient term in the direction that the function is getting maximized? Then in practice, this is really not happening. So like older days when people just implement everything from scratch, this was a kind of node people should pay attention. But really nowadays, that is not happening. Okay? So moral of the story, it's almost never, but this almost is less emphasized as compared to the other cases. Almost never you get trapped in the saddle point. Okay? Everybody's cool? And the moral of the story is that when you use gradient descent, in practice, you almost always end up with one minimum. But that minimum could be a global minimum, which is the best thing you could get, or a local minimum, which is the case most of the time in practice, right? So in practice, your function has so many minimizers that you can never guarantee that you end up with a global minimum, but it's okay as long as you end up with a fine local minimum. Any question on that? No question? Okay, so if you got no question, then one last thing about the algorithm, the gradient descent, is the importance of this learning rate, right? And this learning rate is very important in how you choose it because its value can impact the convergence of your original algorithm, and you can guess. This means that even if you are using the gradient descent and your algorithm is always moving towards the minimizer, there is no guarantee that you use it with any step size, any learning rate, and it's going to end up with a minimizer. You can still get diverged if you do not choose it properly. So let's think about this learning rate to get a bit of clue about this. Then we're going to leave it here. We just get back to this again in chapter 3 when we want to just improve our knowledge on optimizers. Now, say that I am at this point, and I start from this point, okay? Now, I just choose one step size, one learning rate, which is just taking me this much, okay? One question, if I move, I'm going to end up at this point, right? At this point, what would be the step size? If I keep the learning rate fixed, if I keep eta to be fixed, I am moving this much here, right? What about this point? Am I going to move the same? I'm going to move the less. Everybody sees that, right? Why I move less? The gradient is decreasing, right? So everybody sees that, right? Everybody's cool? So when your learning rate is fixed, it doesn't mean that in every step you are moving same step size, right? So that eta is fixed, right? Look at this algorithm here. Very important at this point. Where is it? Eta is fixed, but this guy, the value of this guy changes at every single point, right? So it's not that you get a fixed size gradient every time, right? The more you get close to the minimizer, like the more you get close to the minimizer, the smaller your step gonna be, right? Because the gradient gonna get smaller. Yes. Learning rate. Eta? Yes.
You're saying so eta in W frame or whatever is the same, but you're saying is the delta y gets smaller?
gradient, delta y. Right, delta y, or the f prime, the derivative of your function, right? The derivative of your function here is the slope, right? It's large. When you get here, the derivative is very small. It's getting to 0, close to 0, right? And then you get that derivative, you multiply it with eta, right? Learning rate. If learning rate is fixed, still your steps are going to shrink, right? So now, I started with this step, right? And go forward, right? So next step is going to be smaller because I'm getting close to the minimizer. And then I keep on going, so on, till I get very close to that, right? I'm going to land there, right? So if my eta is very small, I'm going to land to the next minimizer, for example, right? So that is the case. So there is always some guy like eta star, which is a threshold. It doesn't mean that you can compute it. If the function is very simple, you can compute that eta star. If the function is complicated, as it's always in practice, you do not know what is that. But you do know that there is a value when you are below that, your algorithm is moving towards the minimizer, right? Now, say that we know that eta star, like for example in this case, this is going to be something like this, right? If that is eta star, which at this particular point is going to just take me exactly to the minimizer, right? And then after that, the algorithm stops, right? So if I move by any step smaller than this guy, then I am going to get to this particular point, right? But what's going to happen if I just take my learning rate a bit larger than that? We start to oscillate, right? So if I take it larger, then maybe I take this one, then I'm going to get to this point, right? At this point, the gradient tells me just go back, right? So I'm going to get back, right? And it gets smaller, of course, because I'm lower towards the minimizer, right? And I keep on just moving till I get to the minimizer, right? So I'm oscillating around the minimizer. Is it still okay, right? Right? So this is the case when I exceed that eta star. But still, I am below some maximum possible values, right? This is what I'm going to call it eta threshold. So eta threshold on this simple curve is essentially the step size, which is going to take me exactly to the other point, right? If I get exactly here, then the gradient is going to move me back here, back and forth, right? I keep on oscillating between these 2 points in this very simple curve, right? In practice, the curve is much, much more complicated, right? But in this very simple curve, I'm going to oscillate here, right? Now, if I am below this threshold, then I keep on oscillating till I get exactly to the minimizer, right? But what's going to happen if I exceed this threshold as well? It's going to be? It's not going to converge. It's going to get out of the bowl, right? So say I just take larger steps, so I'm going to get here, then I see what is the function here, so I'm going to get back, and I keep on going till I get out of the bowl, right? So there is always, when you are using your gradient descent algorithm, there is always one optimal step size, which is going to just move you exactly to the minimizer. You don't know it because you don't know exactly how the surface looks like, right? But if you exceed that, it's still okay. If your bowl is very deep, right, you're going to keep oscillating around it. But obviously, if you take your step size, your learning rate too much, if you take it very large, then you're going to get out of that bowl. Doesn't matter how deep that is. You can always take one very large step, and then you start coming out of it, right? So moral of the story, it's very important to choose the right learning rate. If you don't choose the right learning rate, then your algorithm can easily diverge. Okay? Questions? No question? Okay, great. So now, if you have a multidimensional case, which is always in practice the case, then of course these optimal learning rates are going to be different in different directions, right? So there is no reason that the bowl that you're looking at is symmetric, right? In one direction, for example, you think of a two-dimensional curve, right? The cuts, the contours that you look at it, could be some ovals of this form, right? Then the optimal size that you want to take in one direction is this much, but in another direction is this much, right? Same thing for the maximum size that you can take, right? So that one, when you get a high dimensional function, every single w in that function going to have its own specific maximum possible learning rate, right? Now, if you want to do the update, some easy thing that, or some efficient thing that you can do is this guy, right? So you would say that I do not have just a single learning rate. For every single entry, every single parameter in my model, I have its own specific learning rate, right? But one question, do you think that this is a feasible approach in practice? No, because in practice you have in the order of, I don't know, 10 to the power 7, 10 to the power 8 parameters. Then you need to have this much of learning rates, right? That is not really feasible to just coordinate all of them. So what we do in practice, if we don't want to do any learning rate scheduling, then we usually do something like this. So we would say, okay, what is the allowed learning rate for every single direction? Then I'm going to keep, if I really want to end up with that minimizer, I'm going to keep my learning rate below the minimum one, right? And this means that for every guy, I'm going to converge every single direction. So there is no direction that I could just diverge in that direction and get out of the bowl, right? So you can do this, typically, if you want to just use one single learning rate. But actually, we can indirectly implement this idea, and we're going to do it later in chapter 3. Okay? This is, for instance, what we do by RMS prop. Okay? Everybody's clear? Questions? So right now, the only thing that I want to give you is that you just have this idea in your mind that learning rate is the most crucial thing in this algorithm that is going to make your algorithm to converge or diverge. Okay? Now, one thing that we can conclude out of it is that there is some sort of, threshold here. If I take my learning rate quite large, then of course every single step that I'm taking is larger, so potentially I can converge faster. But the issue is that, as you have seen, I increase the chance that I just get out of the minimizer, right? I just miss the minimizer and go forward, right? So there is the chance that I just diverge, but on the other side, get a faster convergence if I do not diverge, right? And if I choose the learning rate is smaller, then of course the chance that I diverge is going to get smaller, but on the other side, I need to wait more to get into the minimizer, right? Clear? Questions? No question? Okay, great. So now, you might tell me, okay, let's say we're patient, we are not in a hurry, we can just wait till it converges, then the safe choice is always to choose very, very small learning rate, right? Do you think this is a right argument? It's only a right argument when your function is convex, the function that you are minimizing. Because then you are sure that you're always going to touch the only minimizer that this function has, so it's always fine that you just move with the step, with very small step size. Okay? But in practice, the functions that you have in deep learning, they are never convex. And because of that, this is not necessarily a good idea to move with a small learning rate always. So let me just clarify this one. First of all, this is a convex function. You don't really need to pay attention to this definition here. If you like, you can check it later, but the only important, a function is convex when it looks like this, right? Anywhere you stay on that function, you're going to just, slip to the minimizer. And there is one minimizer for this function. This function could have multiple minimizer, but if it has multiple minimizer, it's going to look like this. It's going to down, then flats, and then go up, right? So then the minimizer are not different, right? They're essentially the same thing, all of them, right? So it's kind of land which has just one valley, right? That is convex. Now, if you have this convex function, then this makes sense that you have always one minimizer, right? So this is what we say. There is no disjoint local minimizer in this convex function. It cannot be that you have here, then you go up again here, right? two disjoint minimizer. This is never going to happen in a convex function, right? So if you end up with one minimizer, every other minimizer, if any, is around it, right? That's it, right? So there is always one bottom to the whole curve, the whole surface, right? And then it makes sense that you start any point and you use gradient descent, you're going to end up there if you have a very tiny step size, right? So this means that if you choose a small learning rate, you always converge to the minimizer. And that minimizer is not only the local minimizer, but it's also the global minimizer, right? So it's globally the minimum of the function. But you should be so lucky to have such a function. In practice, you would never have it unless you're using the dummy models like linear model, right? So in practice, what you're going to have is going to be a super weird landscape, something like this, if you want to think one-dimensional. Like you're going to have huge number of minimizers, right? So if you want to think high-dimensional, then you're going to be like these weird spectrums that you see, like full of minimizer going up and down, right? Like the mountain, like Alps, right? It has lots of peaks and lots of valleys there, right? And depending on where you start, if you use gradient descent, you're going to end up with one of them, right? One of the valleys, right? So this is the case in practice. So in practice, you have lots of local minimizers. And if you want to just choose a small step size at any point that you start, you're practically going to end up with the next minimizer, right? But there is no reason that the next minimizer is necessarily the best minimizer, right? Maybe it's a very, very high and very bad minimizer, right? And then it has a very smooth curvature, right? Yes?
But isn't it completely random? Even if you choose a bigger pace, let's say, right?
Yes.
Even with that, it only depends on, it's random, right?
It's somehow random, that's true, but at the same time, in this curve, if you think, right? If I take some larger step, okay? Because here, you're going to have faster gradient decay, right? And this one could potentially take you lower, right? But this one, when you start, then you are not going to jump this one anymore, right? So this is the reason that I tell you that this is not always the best idea that you may take the smallest one, right? But is it random that we end up with one minimizer? Exactly, that is the case. Now, what we do in practice we use extremely high, large models, right? Extremely overparameterized. And then those extremely overparameterized going to have extremely large number of local minimums, right? And when you increase that number of local minimums very large, those local minimums start to get as good as each other, right? So if you have a two-dimensional surface, say your model has only two parameters, then you might have one minimizer here very high, one minimizer here very low, right? And you want to end up there, but as you said, it's quite random. You cannot guarantee that you're going to end up there, right? But if you make it like extremely high dimensional, like instead of two parameters, you have 100 parameters. Now you're going to have very large number of minimizer in that 100-dimensional function. And then the difference between those minimizers is going to get smaller. Then you don't care. You just end up with one of them, right? This is why when you have extremely high capacity model, like very deep neural network, it's going to capture something, right? Because you definitely are ending with one local minimizer, but that is good enough for you. You don't care that you can end up with a better one, right?
Why does that happen? The more you increase the...
Yeah, this is a bit of complicated thing to explain, but this is a kind of property of the system. So you can think as in like thermodynamics, like when you have too many particles interacting each other, then they start to somehow get into equilibrium, which makes more sense. Like if I have two particles and I just hit them together, then they're going to hit each other, go other direction, right? And then I would never end up finding them, right? But if I have billions of them and I just hit them, they're going to start hitting each other, and they're going to remain within this area, right? This is a sort of overparameterization property. There is a very long mathematical literature on it. Many people still work on it to just explain it in details, but this is something that you see in practice. Questions? No question? So, key point, if you have non-convex function, which is always the case, this is not necessarily a good idea to take very small step size, right? So you don't want to start with 10 to the power minus 8 as the learning rate. Yeah? It might be that this is a good choice, but you might, I mean, even if you see it's converging, you might want to just increase your learning rate once and check whether it is still converging and is converging to a better point. Because if I increase it, it might happen that I just pass this bad minimizer and I get to a better minimizer, right? That could happen. How you can find it? Well, as we discussed with your friend, this is quite random, right? But you want to check it. Yeah? You don't want to think always that best learning rate is the smallest one, right? So, questions? Everybody's clear? So, you can add to this trade-off that I told you that when you use large learning rate, in addition to those two other things, which was one of them was the high chance of divergence and the other one was a high convergence speed, you have this chance that you pass one local minimum, which is a bad minimum, and you end up with a better local minimum, right? This could happen, right? Whereas when you use it extremely small learning rate, then this probably not going to happen. You're going to just land to the next minimizer, and it's totally depending on your chance whether it's a good one or not, right? Everybody's clear? Questions? No question? Okay. Now, how we can do it in practice, like a very conventional way, is that you typically, when you want to code, you just start with a large learning rate, and then you can gradually decrease it, right? And you can even do it within your algorithm. Like in the first steps, you take large learning rates, and gradually you start to decrease it. This is what we call it learning rate scheduling. And this is something that we're going to discuss in details along with the other optimizers in Chapter 3. Everybody's cool? No questions? So in Chapter 3, we're going to get back here. By that point, you just don't have any question about gradient descent anymore. You just want to see how you can make it more efficient. And then we try a few ideas which are quite well known. OK, so if you got no questions, so this is the final summary of the whole thing. So this is the algorithm. The key point is always the gradient. This learning rate is going to be quite crucial. If the function was convex, we could have ended up with a global minimum. We cannot do it because the functions are typically non-convex. And the key point then is to just play around with this learning rate to make sure that you're ending up with a good local minimum, right? So, moral of the story, gradient descent always works, but it's going to end you with one local minimum, right? So don't do this mistake that people say, oh, gradient descent only works when the function is convex. No, it always works. It always ends you with one minimizer, right? But you don't know that minimizer, whether it's a good minimizer or not, when your function has so many minimizers, right? OK, so then, everything that we have in practice is always based on this gradient descent. You're going to see it in Chapter 3, so no worries about that.